Right, well, good evening, folks, and welcome to the Dublin Institute for Advanced Studies, and welcome, I think it's the last of our Samhain August Science events. So these have, Samhain August Science, we've been doing this for 6 years now, and obviously we try and bring in a sort of Samhain or Halloween type theme to the science and also the, shall we say, Celtic studies element of this this festival. So it's a case of dark matter and dark matters as well, that this sort of thing that we will cover. So this evening, before I introduce our speaker, who's going to tell us about spooky worlds elsewhere. I sometimes think this world is spooky enough, but there are other ones. So before I do that, let me just point out where the exits are. Obviously, you came in from downstairs, and in the event of any fire alarm or emergency, please just proceed down the stairs and go out the same exit where you came in. The other thing to point out is there are, if you need them, there are facilities, there are toilets, male and female toilets downstairs, but also up here, there are gender neutral toilets as well, if you need. So this evening, it's my great pleasure to introduce Dr. Johanna Vos. Now, Johanna is originally from Ireland, actually did her undergraduate degree in Trinity, and then moved on to Edinburgh and moved to the US then, where she worked in the US Natural History Museum in New York, which actually has a sort of research division, including astronomy. So she worked there and then came back to Ireland, working for a while in the Dublin Institute for Advanced Studies, but now Johanna is based in Trinity. She's used a lot of different telescopes around the world, and also up above. So the James Webb Space Telescope, Spitzer, and as I said, ground-based telescopes like the European Southern Observatory facilities. So she has a lot of experience in trying to look at other worlds. Her particular speciality is what we call brown dwarfs, which are basically failed stars. But brown dwarfs are so small that there is a certain similarity, which no doubt Johanna will explain in more detail, with objects like Jupiter or planets around other stars. Now, some of these worlds are pretty spooky, as you're going to hear this evening. So as I said, it's my great pleasure to introduce Johanna to talk to us this evening. Thank you.
Great, thank you so much for that introduction, Tom. So yeah, thanks all for coming. It's so nice to see so many people excited about the kind of science that I've been doing. So let me just see if I can move my slide, would help. Okay, I'll do it here. So yeah, in honor of the Samhain August Science Festival, I thought it'd be apt to take a quick tour of some of the kind of more nightmarish worlds that we've discovered beyond our solar system. But before we go into that, I want to kind of take you back to our recent history. I want to take you back to the year 1995. So I think most of us in the room were alive in 1995. Some people maybe weren't. But I think anyone who was there can confirm, like, this was quite recent. And back in the year 1995, if you can remember, we knew we lived on planet Earth. That's pretty good. We also knew that there were 7 other planets that orbited our sun. So it was us and these 7 planets, we were orbiting our sun, it was all very cozy. But in the entire universe, this was it. This is all of the planets that we knew about in the whole universe. And we had ideas that there probably were planets beyond our own, but at this point in time, we had never seen any. And then if I'm gonna take you to our view today, and this video I'm about to show you was made using OpenSpace, which is an open source data visualization software that we used at the American Museum of Natural History, which is home to the Hayden Planetarium. So in this video, we're going to zoom out from planet Earth. That's the orbit of the moon you can see. But we're going to keep zooming way out of Earth. You'll start to see the orbits of our 7 neighbor planets come into view. And we're going to keep zooming out way beyond the solar system. And you'll start to see in the background, we can see these stars in the background. And we have actually looked at a lot of these stars since the year 1995 to try and look for evidence of exoplanets. So we're going to keep on zooming out, and in a second I'm going to show you. So now all of the stars, the screen isn't the best, but there are lots of stars there, but all of those blue circles are showing you stars that host at least 1 planet. So, you know, we've looked at a lot of planets, and planets do seem to be quite common beyond the solar system. And just in a second, I'm going to show you another population of planet hosting stars. You're going to appear in yellow in a second. So over there is a portion of the sky that we've really studied intensely. That's called the Kepler field. And we've discovered about 3,000 planets just in that area over there. But we're actually going to keep zooming out because I really want to show you the context of what we've actually seen so far. So we're going to keep zooming out, and we'll start to see lines. Maybe I can't tell if we're going to see it in this video, maybe we won't. So we're going to keep zooming out. Right now, the scale of this is about 5,000 light years. So you can see that that little area we've surveyed is really, really tiny. So we're kind of in this little corner of the Milky Way. And as we keep zooming out, you'll see that even though we've really been looking all around us in our solar neighborhood for these exoplanets, we've really only scratched the surface of exoplanets in our own Milky Way, and we have absolutely no idea about the exoplanets beyond our Milky Way. So that's just to give you a bit of concept about the objects or the exoplanets we've discovered to date. So we now know of over 5,000 exoplanets. And these 5,000 exoplanets that we have discovered, they really show a great diversity. And some of them range from these kind of small, rocky, terrestrial-like worlds, all the way up to gas giants that are kind of more similar to Jupiter. And out of all of these planets, we haven't actually found one that convincingly resembles planet Earth just yet. And also out of all of the systems that we've discovered beyond our solar system, we also haven't found a system that looks like our own. So even though we have found all of these new exoplanets, I think it's still a little bit lonely where we are. And most of these 5,000 exoplanets, most have actually been discovered using what I would call indirect methods. And this means we haven't actually seen most of these planets, but we do know that they're there. And I guess the most popular method for detecting exoplanets is called the transit method. And this is where you observe a star very precisely, you measure its brightness. If you keep watching its brightness over time, you might measure a dip in the brightness of the star. And this dip is caused by an exoplanet that's orbiting around that star that happens to cross the face of it. And thanks to several kind of space-based dedicated missions to look for planets using this technique, we really have a lot of transiting exoplanets we've found. One of these dedicated space-based missions is called the Kepler mission, showing you Kepler there on the left, and you can see the Kepler field. Let me see if this is woken up. There we go. You can see the Kepler field just there. So that was all of those yellow planet hosting stars I showed you were in that region. And basically Kepler just stared at that patch of the sky for 4 years, and it measured the brightness of nearly 500,000 stars during that time. And that allowed it to discover about 2,600 planets during the mission lifetime. And I just want to point out that, you know, there's kind of nothing that special about this region. We know there's a lot of exoplanets there, but if we just had happened to point Kepler in another direction, we probably would have found the exact same number of exoplanets in that direction. So while in that video I showed you, it probably looked like there was loads of planets in that region of the sky, it's only because that's just where we've looked really, really intensely. A second kind of popular indirect method is called the radial velocity method. And again, we're never actually seeing the planet when we use this method. So here again, we observe the star, but this time, instead of just measuring the brightness, we're actually measuring the spectrum of the star over time and seeing how that spectrum might change. And this video is kind of showing you a bit of a cartoon version. So using that spectrum, we can measure something called the radial velocity. And that's basically the speed with which the star is moving towards us or away from us. And basically as a planet orbits around the star, it's actually pulling on that star the whole time. And it pulls it around in its orbit. So I'll just show you again. You can see that the star, it's not actually staying in the exact same position. It moves slightly as the planet kind of pulls on it. And we kind of call this like the stellar wobble. And this wobble can be very, very slight, and it can be hard to detect, but we have actually measured a few hundred exoplanets using this technique. And this is just a little illustration of the radial velocity method. So you can see when the star moves towards you, the spectrum is kind of shifted towards this blue end. When it moves away from you, the spectrum is shifted towards this red end. And I guess this diagram kind of nicely reminds us that we're not actually observing the planet. We never see the planet when we do this. We're just observing the planet's interaction on the host star. So we know the planet's there, even though we don't see it. And then finally, the last technique I'll talk about today is called the direct imaging method. And this is the method that I use. So I'm going to try and not be very biased, but this is my favorite, so that'll probably be apparent. But this is a direct way of detecting and observing and understanding exoplanets. So in this method, we're actually taking an image of a planet. So it's the only direct method there is. And while that sounds quite simple, it's actually one of the most challenging techniques because separating the star's light from the planet's light is really, really difficult. Since your planet is right beside that really bright star. So in the very best case scenario, your star will be about 10 billion times brighter than your planet, and you're only after photons from your planet. So if you can imagine you're trying to image this kind of Saturn-like planet orbiting a sun-like star, the planet's going to be completely lost in the glare of its host star, right? So makes it really hard to find it. But we have come up with these techniques to try and get around this. And one of these techniques is shown in this video. We can put this little disc, which is called a coronagraph, inside our telescope. It blocks out 99.9% of the light from the star. And there is some light left over. You can see it kind of coming out from behind the coronagraph. But if we block enough of the light, we can actually see the planet glowing there beside it. And this is a very difficult way to study exoplanets. We have a pretty small number of exoplanets that have been discovered using this technique, but it's really worth it because this is the only technique that's giving you photons directly from the planet's atmosphere into your telescope. So it's giving you really direct and powerful information about the physics of planetary atmospheres. And as I said, out of these 5,000 exoplanets, we still haven't found a world similar to our own. And in fact, most of the planets that we found are pretty scary. So today we're going to kind of explore some of the more nightmarish worlds that we've discovered. As I said, I'm trying not to be biased tonight, so I've picked a transiting planet that is doomed. I've picked a radial velocity planet that's kind of pretending to be an Earth twin. And then I picked 2 direct imaging discoveries. So one wide orbit exoplanet with kind of wild weather, and then one very cold, isolated world. So we'll go through each of them and see if we find one better than Earth. So first I'm going to talk about the planet WASP-12b, which, as I mentioned, is doomed. And WASP-12b was discovered using the transit method. So scientists stared at the host star over a long period of time. Every so often they measure this dip in brightness as a planet orbits in front of it. That planet is called WASP-12b. And by figuring out how often these dips happen, you should get one dip every time the planet does one orbit and crosses in front. You're able to calculate how far the planet actually is from its host star. So they did that. And to kind of give you a sense of scale, let's consider the distance between the Earth and the Sun. So we're situated about 150 million kilometers from our Sun. And that's quite hard to kind of picture in your mind. So I'm going to try my best to explain to you that distance here. So if you can imagine if the Sun-Earth distance, and astronomers, we've come up with this unit called the astronomical unit. So we are 1 astronomical unit away from the Sun. It's the same as 150 million kilometers. So let's assume that 1 astronomical unit takes up 3 slides. So if you're at the Sun and you want to get to planet Earth, you have to travel the whole length of this slide, the whole length of this slide, and then the whole length of this slide, and then you get to planet Earth. So that's 1 AU, and we can all picture this. On that scale, the distance between WASP-12b and its star is only about this size. So it's about 2% of the distance from the Earth to the Sun. And that means actually that it takes just over a day for WASP-12b to do 1 entire orbit of its host star compared to our year on Earth. So this thing is whipping around very, very quickly. It's very, very close. And it turns out that has some pretty spooky consequences for this exoplanet. So since WASP-12b is so close to its host star, it's experiencing this enormous gravitational pull and these tidal forces from its star. And these forces are so strong that it's actually turned the planet into like the shape of an egg. So over here is what we call the day side of the planet, and it's always facing the star. And that is heated to over 3,000 degrees Celsius. And then over here we have the night side, and that's just in permanent darkness, and it never ever gets to see any light from the star. And as this star keeps pulling on this planet, it's pulled it into this egg shape, but it's also stripping material off the surface of the planet. So it's kind of slowly being devoured by its host star. And these people, led by Lee et al., they calculated that about 190 quadrillion tons of material are being pulled off this star every year. So, its days are quite numbered. And that material isn't actually being pulled straight onto the surface of the star. It's actually probably forming this kind of ring. So it's kind of like the guts of this planet are forming this ring around the star. And we think that this is probably composed mostly of carbon because that's what the planet is made of. And all this does sound pretty terrible already. But the final nail in the coffin for this exoplanet is that its orbit is actually decaying. So by measuring the time between the transits over the last 10 years, it turns out that time is getting shorter and shorter. So this planet is getting closer and closer to its host star over time. And it only has about 3 million years left before it completely merges with its host star. So as I said, it is doomed, so we can't move there. Okay, for our second exoplanet, I wanted to share a story bit of a troubling tale of an apparent Earth twin that's actually orbiting our nearest neighbor, Proxima Centauri. So this is our closest star to our own solar system. It's located about 4 light years from the sun. So it's really our neighbor. So it would be really nice if we had an Earth-like planet there, because it's potentially the only one we could ever visit. And the star itself is called a red dwarf, so it's a pretty small star. It's about 3,000 degrees Celsius, as opposed to maybe 5,500 for our own sun. So it's kind of a small, dim star. And this was discovered using the radial velocity method. And I wanted to show you the actual data here, because it's really incredible. To remind you, what we're looking for here is the movement of the star towards you and away from you. So all of these points here are the measurements of the speed of this star at various times over the phase of the planet's orbit. So this planet actually orbits its star every 11 days, so not as bad as WASP-12b. On the y-axis is a measurement of the speed. So I put in this kind of pink line at 0. So anytime the points are below 0, it means the star is moving towards us. And anytime the points are away from 0, it means the star is moving away from us. And if you actually look at the y-axis here, we're measuring a movement of about 1.8 meters per second. That's about the speed we walk at, okay? So like, this is not a huge signal that we're measuring. Like the star is very slowly moving towards and away from us, but we've built these amazing instruments that can actually allow us to measure that tiny difference. So that is the stellar wobble of the star that tells us there's a planet there. And using the shape of that curve I just showed you, astronomers can actually come up with the mass of the planet. So if there was a bigger planet, the wobble would be more. So it's a pretty small wobble, so it means it's a pretty low mass planet. And it turns out that Proxima Centauri b, which is the planet's name, has a mass of about 1.3 times that of our Earth. So that's pretty similar. It is very, very close to its star. So I told you it has an 11-day orbit, as opposed to the Earth's 365-day orbit. However, it's not as bad as the case for WASP-12b, because as I told you, the star is actually smaller and dimmer and fainter and cooler. And it turns out actually that Proxima Centauri b is in what we call the habitable zone of its host star. So the habitable zone is what we calculate as the region from a star where liquid water can be stable on the surface. And we figure, for life as we know it on Earth, we need liquid water. So because this star has a temperature of maybe 3,000 degrees Celsius, you have to be quite close to your host star to get that temperature to have water. So Proxima Cn b is right there in the middle of the habitable zone, right where you can have water. It's the same size as Earth. That worked for us. So you're probably wondering why it's in this talk at all. It sounds like a lovely place to be. But it's not. Unfortunately, the planet's host star poses a huge problem. So as I told you, Proxima Centauri, which is the host star, it's a red dwarf star. So it's a very low mass star. It's cool, but don't let that fool you. These M-dwarf stars are actually very inhospitable for any forms of life, or really any planets that are orbiting them. Because they give out these huge bursts of radiation called flares. And in fact, Proxima Cn b was recently observed to exhibit the biggest flare ever observed on any star ever. So using 2 different telescopes, ALMA on the top, which observes in sub-millimeter rays, and the Hubble Space Telescope, which observes in the UV, which we all know is not very good. That's why we all wear sunscreen. So UV is very dangerous for people, or any form of life, really. So during these observations, we have time on this x-axis, So they were observing this star, it was normal, 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 and then all of a sudden there was this huge peak in both of these wavelengths. In the sub-millimeter wavelengths, the star was 1,000 times brighter than usual, and in the UV it was 14,000 times brighter. So if you can imagine the UV rays coming at you being 14,000 times stronger, like, you know, your factor 50 isn't going to do anything. You're kind of doomed. So these frequent super flares emitting this kind of radiation can erode any ozone layer in a planet that's trying to protect any life on the planet. And in fact, it will also just completely erode the atmosphere of any planet. So it's likely that this planet just doesn't have an atmosphere at all. So there's no air to breathe, there's nothing to protect you from these rays. So it's probably not a great place to be. However, you know, since this planet has only been detected indirectly, we've never seen the planet, we've just seen the star moving, we actually have no way yet of trying to figure out whether or not it still has an atmosphere. So maybe in the next 10 to 15 years, we will be able to direct this planet eventually directly. But until then, the fate of Proxima Cen b is a bit of a mystery. But I'm not holding my breath. So the third exoplanet I want to talk about is a directly imaged exoplanet that was actually discovered by a citizen scientist. And this is the team that I've been working with for many years. So here I'm showing you an image of the field using the WISE telescope. So this is the kind of zoom out versions showing you the host star in the center and kind of its neighboring stars. You can zoom in on the star, you see it here. And then if you zoom in on this little box, you can actually see this planet. You can see photons from the planet directly. So the citizen science project is called Backyard Worlds Planet 9. It's a NASA-funded initiative that aims to find cold worlds both inside and outside our solar system. So I'm playing with my microphone here. So far we've had about 70,000 volunteers help us, and we've actually been really successful finding these kind of cold, mysterious worlds. And basically what our volunteers do is look for objects that are cold and nearby. And the thing about things that are nearby is they appear to move very quickly on the sky. And we call this high proper motion. So it looks like these things are moving very fast from our vantage point. And this video kind of shows how this works. So here I'm going to show you a video of a star called Barnard's star. It's actually the fastest star moving in our sky. And if you observe the same patch of sky over and over again for like 20 years, you'll see that all of these other stars remain in pretty much the same place, whereas Barnard's star is moving compared to the background. And that's because it's very close to us, and it just appears to be moving faster than these very distant objects. And basically we give images to the citizen scientists, and they flick through the images and try to look for these moving cold worlds. So Backyard Worlds, we use images from the Wide Field Infrared Survey Explorer telescope called WISE. This is an amazing telescope. It takes an image of the whole sky every 6 months. So then we can just take those images and we have this movie where there's a frame every 6 months over the course of, you know, as long as this telescope is still going, and it still is. So it's been going nearly 10 years at this point. On the right-hand side, I'm showing you the discovery of this directly imaged exoplanet called BD plus 60b. So I'll kind of turn the movie on. And basically from 2010 to 2020, over the course of 10 years, this is the star itself. It looks quite strange because it's completely saturated in the WISE telescope. So it's like if you tried to take a picture of the sun with your iPhone, it actually looks something like this. But it has this high proper motion, it's moving, and it also has this companion moving with it. You can see these more distant stars are staying put. I never quite understand how these citizen scientists notice these things. I'm always staring at these images and wondering how they notice them, because they're looking through thousands of images. But this one turned out to be a very exciting world. So after the discovery, we actually decided to follow it up with the Hubble Space Telescope to try and figure out what was going on in its atmosphere. And as I said earlier, these imaged planets, we're getting photons directly from the atmosphere. So we can actually gain a really detailed view of the atmosphere. And if we actually just stare at these objects for a very long time as they rotate, you can actually measure these brightness changes caused by clouds rotating in and out of view. So in this video here, I'm showing you an artist's impression on the top, and these are real brightness measurements taken with a telescope. So if there's a dark cloud that rotates into view, there's this kind of dip in the brightness, and when all the clouds kind of clear, you measure this really bright planet. And so we did exactly that with the Hubble Space Telescope. And we got all of these different light curves and different wavelengths that tell us about the atmosphere. But we found these really dramatic variations, and these are caused by clouds rotating in and out of view. It also allowed us to measure the rotation period of this object. So it's rotating about every 10 hours, which is the same as Jupiter. So it's kind of like a young version of Jupiter. However, we could also try and figure out what is in its atmosphere. And this object is actually maybe a little bit too hot for us to live in. The temperature of this object is probably around 1200 degrees Celsius. So instead of the lovely water clouds that we take for granted in Ireland, the clouds in this world are probably composed of molten iron droplets and vaporized like sand in the atmosphere raining down on you. And then we can also measure all these nice molecules in the atmosphere. So it's probably not the best place to be. And if you're wondering kind of what these condensates are, so we have, we have these things on Earth, but they're solid, right? So we have iron, we have, this is magnesium silicate called forsterite. But in the atmosphere of this object, it's so hot that they're liquid or kind of grains in the atmosphere. So again, probably not a great place to move to. And then last but not least, I wanted to introduce you to this isolated world called Y0855. So it was discovered with the WISE telescope, that's why it's in the name. And this is actually another one of our neighbors. Oh, there it is. So this is located about 7 light years from us. So that's actually, in the scale of our Milky Way, that's actually very, very close. One weird thing about this object is that it's very, very close to us. I guess it's our 4th closest system to our solar system, but it was discovered less than 10 years ago. So it's kind of just been there lurking, and we only just found it recently. And as I said, it was discovered with the WISE mission and the Spitzer Space Telescope. Using this technique I kind of talked about earlier, where we're looking for high proper motion objects, which tell you that it's close by. So this one's maybe a little bit harder to get to grips with, because the first 2 images are from the WISE telescope, and the second 2 images are from Spitzer. And Spitzer is a bigger telescope, so it kind of gives you a sharper view of the field. So back in 2010, your object is here, and then by the time we look at it with Spitzer, it's over here. It's hard to make out the kind of the steady objects, but these 2 kind of remain steady, and you can see them in both. So Y0855 appears to be moving very quickly, and it's also very dim, so that told us that it's actually probably very cold. And it actually turns out that this is the coldest world that we found beyond our solar system. It has a temperature of about -20 degrees Celsius. So it's kind of like the North Pole on a kind of a warm day, actually. So this is, these are temperatures that maybe some people here have felt themselves. We think that there are clouds composed of water in the atmosphere. So that seems pretty good for a new place to live. -20 isn't great, but it's not terrible. So maybe this is somewhere we could live. Unfortunately, the problem is that Y0855 doesn't have a host star at all. So it's just kind of wandering through the Milky Way on its own. So without a host star, there's no light, there's no heat. So, you know, there's no plants, there's no life. It would be pretty hard to live on this planet. And even if maybe you could figure out a way to make life work here, the problem is that this world is actually getting colder and colder over time. So while it's minus 20 degrees Celsius now, it's going to be a lot colder in a few million years. And it'll eventually be so cold that we just won't be able to see it anymore. It will just kind of disappear from view. So, you know, planet Earth is actually pretty okay. I know we don't always think that, but we're at this really nice temperature that can support liquid water, which in turn support life as we know it. We have this atmosphere full of all the necessary molecules for us to breathe and to function. And we have this great ozone layer protecting us from UV rays from the sun. And then the sun actually isn't all that bad either, considering all those other M dwarfs out there just completely destroying their planets. So we're kind of in this really nice spot. However, we haven't given up the hunt for Earth-like planets just yet. And I think that the next generation of telescopes will really allow us to discover worlds that are more similar to, you know, our own planet Earth. So I just wanted to quickly point out the extremely large telescope. We're not very good at naming things. I don't know if that was apparent already. Astronomers, we're not very imaginative. So this is the extremely large telescope, successor to the very large telescope. And this is going to be the world's largest telescope. And this is just an artist's rendition of what it will look like when it's all done. And it's located in the Atacama Desert in Chile. So its primary mirror, which you can kind of see peeking out here, that measures by 39 meters across. So this is almost 4 times bigger than the biggest optical or infrared telescope we have on Earth. So this is a huge step up from what we have now. You can also, actually, you can't even see, there's cars parked here to give you a sense of scale. You can't even see them. I think the height of this whole building is about 100 meters. So it's like a football stadium with a telescope inside. It's in the Atacama Desert in Chile. And I think they had to like blow off the top of this mountain to even have a plateau that they could put it on. So it's absolutely incredible. And then this can kind of rotate around on its axis to look at any part of the sky. And it is actually under construction. So this image, which actually doesn't look great here, but Google it later, it was just released a few weeks ago, and it shows the moon kind of rising behind the structure of the ELT. And once it's built, it'll help us to explore exoplanets through the techniques I've been talking about today, so transit, radial velocity, and direct imaging. So with the radial velocity planets, it's going to, do you remember I told you that Proximus NB caused this wobble of about 1 meter per second on its host star? So that's like me walking forwards and back. With the ELT, we'll be able to measure precisions of 1 centimeter per second. So that's like the speed of a snail moving forward and back. So we're really going to be able to measure these really slight changes, and that means smaller planets, basically. With transits, we'll be able to look for much smaller transits. We'll be able to investigate the atmospheres of those exoplanets by looking at the transit across lots of different wavelengths. And then finally, for image planets, which are my favorite, the ELT is actually going to allow us to image rocky planets that are inside their habitable zone. So potentially something like Proximus NB is something we'll be able to get a direct image of. So this amazing facility is really going to be a huge leap forward in our search for other worlds, and hopefully we'll start kind of finding some familiar worlds as opposed to the scary ones. So thank you very much for listening today. I'll leave you with this picture of our son, which I just told you isn't scary, but it actually looks pretty scary here. So if you have any questions, I'd be happy to answer them. Thanks.